So hi everyone, for another South American geometry webinar. Today we have Gonçalo Oliveira telling us about special Lagrangians, Lagrangian mean curvature flow and stability.
Okay,
Yeah,
so
Gonçalo, please go ahead if you can. Let's do 50 minutes so we can still have some 5 to 10 minute questions.
okay. Thank you for the introduction. So,
Cheers.
as Enrique said, my title is Special Lagrangians, Lagrangian mean curvature flow and stability. And let me start by introducing what the main question of this talk will be about. So we start with a symplectic two n-dimensional manifold. So a symplectic manifold. So that means that omega to the power n is a volume form, so never vanishes, and it's closed. And we will be thinking about a special class of submanifolds, of symplectic manifolds, called Lagrangian Sub Manifolds. So a Lagrangian submanifold is one defined by the condition that if you pick the symplectic form, which is this two form, and restrict it to L, that vanishes. So that is the definition of a Lagrangian submanifold, of a symplectic manifold. And if you like to think of symplectic manifolds as generalized phase spaces of mechanical systems, then perhaps it's also useful to think of Lagrangians as generalized configuration spaces. And usually, symplectic geometers, they regard Lagrangian submanifolds up to an equivalence relation. So usually one thinks of two Lagrangian submanifolds as being equivalent if they are Hamiltonian isotopic. And then I will explain in an example what this means in case you're not familiar. And I'm going to denote by straight bracket L the Hamiltonian isotopic class of L. And then a natural question that you can ask is whether there is a canonical best or interesting representative of an Hamiltonian isotopic class. So is there a best or canonical or interesting, very vague question, representative of these Hamiltonian isotopic class of Lagrangians? Okay, so, and I will motivate the answer to this question, or a possible answer to this question, using an example. And the example is when we are in 2 dimensions and our symplectic manifold is simply the 2 torus. So R2 mod Z2 with the symplectic form that descends from R2 because it is invariant by translations, the dx wedge dy, where x and y are coordinates in R2. And then the condition that L, which is one-dimensional now, be Lagrangian, is that omega, which is the symplectic form, which is a 2 form, restricts to it vanishing. But because L is one-dimensional, any 2 form vanishes there. So this is always satisfied. And so any curve is a Lagrangian submanifold. And now we will see some examples. So let me draw here a torus. I'm going to draw the torus using the square model. So where I'm identified opposite sides. Do I copy? No, this is not what I want to copy. Well, anyway, this is a paste, but then I pasted a citation that I had last copied. But anyway, it's not. Whoa, what is this? Okay, let me go back. Okay.
Or you can cite Lotay in the meantime.
Yes, my computer is not obeying me for some reason. Let me see what I can do like that. Okay, let me try it again. Oops. Okay, that sounds good. Okay, so we have here 3 copies of the 2 torus, and recall we are identifying opposite sides. So this side is the same as these, and these 2 sides are the same. So in particular, the corners are always the same point. In particular, and now I'm going to draw a curve here, which is going to be this straight line. So starting at this point and then coming back to that same point there. So that's a circle. I'll call this L1. And then here I'm going to draw another straight line that goes like that. I'll call it L2. And here I'm going to draw another one like this. This was supposed to be half. Then this point, whoops, what happened? Okay, don't go away now. Okay, and that point is the same as this point, and then we continue with the straight line like that. So I'll call this one L3. Okay, so and then I'm going to draw some other curves. This one, L1 prime, this one, L2 prime, and then this one here, L3 prime. That now starts here. Okay, so these are all circles inside the torus. And the condition that 2 curves in the torus be Hamiltonian isotopic, L is Hamiltonian isotopic to L prime, is that the signed area between them vanishes. Okay, so what does that mean? That means that the area here in blue, so where the blue curve is on top, is the same as the area in yellow where the yellow curve is on top. So that's what that means. Okay, so I have here 3 pairs of Lagrangians, and each pair consists of Hamiltonian isotopic Lagrangians. And then my question is, which one of these ones that I've drawn is more interesting or more canonical? And the answer that I want you to accept is that the straight line is the best one. Okay, so the straight line are the more canonical choice, or are the best choice. Just say that. Of course, in order to say what a straight line is, I'm using extra structure, namely the metric. But let me give you a characterization of straight lines in terms of another object. So in the rest of this example, I will tell you how to characterize straight lines in an alternative way. And I will also tell you how to pick a Lagrangian and then slowly deform it until it becomes a straight line. Okay, so picking a curve and slowly deform it until it becomes a straight line. So first of all, characterize straight lines. So I'm going to start with a complex coordinate on the torus, z equal x plus iy, and I'm going to consider the complex valued one form, which is given by dz. So that's dx plus I dy. And now I'm going to think of L as a parameterized circle there. So by Lx of s, Ly of s, where s is a parameter, which I'm going to pick as the arc length parameter. So the arc length parameter means that the velocity vector of L is norm 1. So this means that Lx prime square plus Ly prime square is equal to 1. And the next thing I'm going to do is to restrict this complex valued one form to L. And what do I get? I get Lx prime plus I Ly prime ds. And because the velocity vector of L as norm 1, this thing that is here is a unit valued complex number. So this is e to the I beta L for some e to the I beta L, so which defines for me a function from L to U1 inside C. Okay, so that's basically cosine beta L plus I sine beta L by Euler's formula. So now if you think of L prime as this unit norm vector, then Lx prime is this thing, Ly prime is this thing, but we know that from here and here that this is cosine beta L, and this is sine beta L. So beta L is this angle. So what we have shown is that beta L is the angle, well, mod 2 pi, between L prime and the x-axis. Mod 2 pi. Okay, so I don't know if this is, I invented this notation. But okay, you understand what I mean. The angle between L prime and the x-axis. Okay, so okay, very well. And so when is it that L is a straight line? So
I think you could call it just the. I think you could call it like the argument of L prime, right?
Sorry. Can you say again?
I think you can just call it the argument of L prime
of e to the I beta L.
Well, beta L is just the argument.
So the argument of e to the I beta L is this mod 2 pi.
That's right. But I'm saying the angle between something and the x-axis. That's right. You're just taking the x-axis to be the polar axis. Yeah, that's it.
Okay, so and when is it that L is a straight line? So L is a straight line if and only if the angle that the velocity vector makes with the x-axis is constant, right? Because that's what the straight line is. So that means that this function, e to the I beta L, from L to U1 is constant. So that's the definition of a straight line. And now the next thing I want to say is, given an initial Lagrangian, an initial curve, L naught, how to deform it until it becomes straight. So the first thing to notice is that if it is possible to do that, then the function e to the I beta L naught would have to be deformed to a constant. So it would have to be homotopic to a constant, which means that there exists a lift beta L naught from L naught to R. So that's a necessary condition. And then how would you do it if this necessary condition is satisfied? How would you actually go? Okay. So let's see here. So remember this curve that we have that was like this, then continues here like that. And we want to deform it to a straight line. The candidate straight line is this one. So what we need to do is to push it along this direction. And that is the direction of its curvature. So if we have some L naught here, this direction here is the direction of its curvature. So the second derivative of L naught with respect to the arc length parameter. So what one does is to pick a family. So we pick a family of curves, LT, which starts at L naught and evolves through the following equation. So it evolves in the direction of its curvature. So this is called the curve shortening flow. And it turns out that the result from Gage and Hamilton in 86 and Grayson in 89 is that if a lift beta L naught exists, then this family LT exists for all time and converges as t goes to infinity to a straight line. Okay, so and now based on these 2 and 1 dimensional example, so 2 dimensions, the dimension of the symplectic manifold, and 1 dimension, the dimension of the Lagrangian. What I will do now is to generalize these to higher dimensions. So see what are the corresponding notions in higher dimensions that we need to think about, and what are the possible answers. Okay, so let's go to higher dimensions. So in higher dimensions, we need not only a symplectic manifold, but as we already alluded to before, there is some extra structure, and that structure is that of a Calabi-Yau manifold. So if you don't know what that is, don't worry too much about it. Let me just tell you one thing that you need to know for what follows is that we have this complex valued n form on M. So that's similar to the omega that we had before, which was a 1 form in 2 dimensions. Now we have an n form into n dimensions, and it is complex valued. And one property of this n form is that if L is an oriented Lagrangian, then if you pick omega and restrict it to L, that as norm 1. Okay, as an n form in L, and with respect to the induced metric on L. But there is another n form on L that has volume 1, which is the Riemannian volume form with respect to the induced metric. So we also have that. So what this means is that these 2 n forms, they must differ by a unit complex number. So there exists a function on L with values in the unit complex numbers such that omega restricted to L is equal to e to the I beta L vol L. So this is an higher dimensional generalization of what we had seen before, where here we had ds, which was the arc length parameter, which is the volume form in 1 dimension. Okay, so we have this function, and now we are going to define our higher dimensional analogs of straight lines, which are called special Lagrangians. So L, as before, a Lagrangian, is called a special Lagrangian if this function e to the I beta L is a constant. So that's the definition of a special Lagrangian. And I'll just comment that these special Lagrangians, they minimize volume in their homology class. Just like straight lines do, right? Okay, so straight lines are in particular special examples of special Lagrangians. And then the next thing that one wants to do is to start with some Lagrangian and try to understand when one can deform it to a special Lagrangian. And also in this situation, there is a necessary condition. And let's see, so if we have some L prime, that can be deformed to a special Lagrangian through Hamiltonian isotopies, or just continuously, then e to the I beta L needs to be homotopic to a constant. And so there exists a lift beta L from L to R, and this is called the grading. And the Lagrangian with the choice of lift is called the graded Lagrangian. So L beta L is called the graded Lagrangian. And from now on, all Lagrangians are supposed to be compact and graded. But the manifold, the symplectic manifold, can be non-compact. Okay, so just so I will not say graded again, but it's subintended. Okay, so before I continue, are there any questions? Just make sure that everyone is okay.
I think we're good.
We're good. Okay. Okay, so now some questions. Question 1 is, given an Hamiltonian isotopic class of Lagrangians, is there a special Lagrangian representative of this class? So that's a question. It's a natural question one can ask. And then the second is, okay, given an initial Lagrangian and a one-parameter family of Lagrangians starting on it and evolving through the higher dimensional version of the curve shortening flow, which is called the Lagrangian mean curvature flow. So that means that if you take dt of Lt, that's the mean curvature vector of Lt. So this is called the Lagrangian mean curvature flow. And then the question is, does this family exist for all time and converge to a special Lagrangian?
Sorry, by dt of L, you really mean a section of the normal bundle, right?
Yeah, so this is a normal vector field, right?
Okay.
Yes, and
if you say so, right? That's a section of the normal bundle.
A normal vector field.
Yeah.
Yeah.
Okay.
Yeah, so which are sections of the normal bundle, indeed. Okay, so now possible answers to these questions were provided in a set of 2 conjectures from Thomas and Shing-Tung-Yau. So conjecture 1 from Richard Thomas says that L admits a special Lagrangian representative. Maybe I'll write it. If and only if it is stable. Okay, so now I need to tell you vaguely what stable means in this context. So stable means that it cannot be decomposed. So it's this Hamiltonian isotopic class cannot be decomposed as L1 connect sum L2. So this is the Lagrangian connect sum. And usually the Lagrangian connect sum of L1 and L2 is different from the Lagrangian connect sum of L2 and L1. So this is not a symmetric operation. And the stability means that you cannot decompose it in this manner with the average grading of L1 being greater than the average grading of L2. So average is not exactly average is average after you take an exponential of it, but I'll just write it in that way. So the average of beta L1 being greater than the average of beta L2. Okay, so that's stability, and this is motivated by mirror symmetry. I can offer some comments about that at the end, if there, or maybe now, if someone wants me to do it now. And the second conjecture from Thomas and Yau. And I'll state the conjecture already with an extra hypothesis that is necessary if it is to be true. And that extra hypothesis is necessary because of the work of André Neves, who proved that if you do not put that extra hypothesis, then this conjecture is false. So I'll already include that extra hypothesis. So it goes as follows. Given L naught, which is almost calibrated, so that's the extra hypothesis, and flow stable, which is slightly stronger than just being stable, then LT exists for all time and converges to the special Lagrangian from conjecture 1.
Can you explain?
So the special Lagrangian from conjecture 1 is unique. Sorry, say again.
No, I was just going to say, can you explain whether this stability condition comes from some sort of GIT quotient? I mean, why do you need this? What does this stability mean, right?
Well, in the
kind of
side,
slope.
In the mirror side for stable bundles, it comes from a GIT from a GIT condition. You can think of it.
What
as
you mean on the mirror side? There's an implicit homological mirror symmetry here.
Well, it's not. The mirror symmetry here is just motivational. There isn't any theorem that says that exactly what happens in the mirror side. You can trace it back here. So these are all conjectures. But in the mirror, when you have vector bundles, holomorphic vector bundles, or holomorphic sheaves, and if you want to be able to find an Hermitian and Engels connection on them, there is a stability condition that comes from viewing the problem as a GIT problem, and from the Hilbert-Mumford criteria for that GIT problem.
Indeed. Hence my question here.
Here in this case, there is no such thing. There is a formal moment map picture, but there isn't. But it's all formal, and it's not, and there is no algebraic structure even. So GIT doesn't quite.
I was wondering why Richard, of all people, would have conjectured this. Since he's an absolute genius of GIT quotients, I was assuming he was performing some sort of quotient somewhere, and that's where he got this from, right?
Well, I think maybe moment maps is more the reason why he was led to this.
Okay, fair enough. Okay.
Oh, but let me tell you what almost calibrated is.
Yeah.
So almost calibrated means that if you pick the total variation of beta L naught, so it's supremum minus the infimum, that's less than pi. So this means that the function e to the I beta L naught takes values in a half space. And if you remember, in the case of curves, beta L naught is the is the angle that the velocity vector makes with the x-axis. So this means that the velocity vector is not changing too much. So it doesn't. So if you do something like this, it would be fine, because you see it never varies more than pi. But if you do something like this, will be bad. If you come like that and then you decide to do like this. So here you are almost horizontal, then you go like that, and then here you go like this. So this is still not. Let me do a worse picture. Okay. So here is almost like that. Here goes like this, and then like this, and that's already more than pi variation, right? Because this guy is almost horizontal, and this guy is already past horizontal in the other direction. So this is bad. This is not almost calibrated. Okay, so that's what almost calibrated is, and it was added because if not, Andre Neves gives you counterexamples. And so, what are the main results? So it's two theorems that prove circle invariant versions of these conjectures, and they are by Jason Lotay and myself, and they are in 4 dimensions with circle symmetry. So there is a circle action that preserves all the structure. Then if you pick an L, a circle invariant Lagrangian, then L is Hamiltonian isotopic through circle invariant Hamiltonians to a special Lagrangian if and only if it cannot be destabilized by a circle invariant configuration. So L is S1 stable. So I'll say again what these things mean. So this means that L can be Hamiltonian isotoped to a special Lagrangian through circle invariant Hamiltonians. And this means that L cannot be destabilized by a circle invariant configuration. Okay, so this is really a circle invariant version of the conjecture, of Thomas conjecture. And then the second theorem is going to be a circle invariant version of the Thomas-Yau conjecture in the same setting. So M4, G, J, omega as before. And L naught flow stable, circle invariant, almost calibrated and circle invariant. Then the Lagrangian mean curvature flow starting at L naught exists for all time and converges to the special Lagrangian which exists from theorem 1. Okay. Again, they are unique. Okay, so are there any questions about the statements of the theorems?
So to be clear, your full manifold with circle symmetry, this means it can be seen as a circle bundle over 3 manifolds.
Away from the points where the action is not free.
Right.
So there is a discrete set of points where the action is not free. Away from that, it is a circle bundle over a string manifold.
Okay. And being destabilized by a circle invariant configuration means that each of the bits in the connected sum have to be circle invariant on their own, right?
That's right. That's right.
Okay, I think it's cool.
Yeah.
That's a nice result. Thank you.
Thank you.
Go ahead.
So now my plan is to tell you a little bit about how the proof goes, so that you see more or less what's going on. So let's do that. So we have the circle acting on our four manifold M. And then there is a projection on the space of orbits. And it turns out that the space of orbits is R3. You can also see this projection as the hyperKahler moment map, if you know what that is. So a Calabi-Yau manifold in 4 dimensions is the same thing as an hyperKahler manifold. And having this circle symmetry that preserves everything means that there is this hyperKahler moment map, and it takes you to R3, which is R3 tensor the Lie algebra of S1, which is R3 again. And so let me draw a picture here of R3. And then there exists a discrete set of points in R3. So these are the points which corresponds to places where the action is not free. So if you have a point in the set, then the pre-image of that point is a point. But if you are away from that set, the action is free, so the pre-image is a circle. So away from that set, it is a circle bundle, as Enrique was saying before. So I'm going to draw here this discrete set of points in blue. So that's S. Okay, so, and again, if you pick one of these points, the pre-image is going to be a point. If you pick this point, the pre-image is going to be a point. But if you pick some point here in the middle, the pre-image is a circle. Okay, so now what is a two-dimensional surface that is circle invariant? So that means that it is the pre-image of a curve. So gamma is some curve in R3. So let's say if I pick this curve here that connects 2 points of S, then above each point of the curve I have a circle, and these circles collapse to points at the end. So above I have a two-sphere. Okay, so that's the picture of the two-sphere above. So the pre-image of any of these points is a circle, and again they are collapsing at the end. If you had picked, for example, downstairs a simple closed curve not intersecting points of S, then above you would get a circle over each point of the curve. And so overall you would get a two torus. Okay, so let me draw it again. Okay, so that's what it would look like. And so then what is the condition that these pi minus 1 of gamma, these curves, be Lagrangian? So that condition is equivalent to gamma being planar. So it lies in a plane. So let's say without loss of generality after rotating everything, you can suppose it is perpendicular to the z-axis. Okay, so, and then what does it mean for two Lagrangians, pi minus 1 of gamma 1? to be Hamiltonian isotopic to pi minus 1 of gamma 2. Sorry, before we go there, one more thing. So what is the e to the I beta L? So this simply corresponds, so beta L is the angle that gamma prime makes with a fixed line in the plane. Okay, so this is very similar to that example that I presented in the beginning. And from this, you immediately see that pi minus 1 of gamma is a special Lagrangian if and only if gamma is a straight line. Okay, so that's important. And now finally, let's go to what I was starting to say. When is it that pi minus 1 of gamma 1 and pi minus 1 of gamma 2 are Hamiltonian isotopic? So this is equivalent to gamma 1 and gamma 2 being isotopic through planar curves. So you need to be able to isotope one to the other through planar curves. So curves lying in the same plane. In particular, gamma 1 and gamma 2 need to lie in the same plane without crossing the points in S. So you can't hit those points in S. So let's see an example. Let's suppose we have 3 points in S in the plane. The plane is my blackboard. So these are the points in S, and I have these two Lagrangians. I have this one called gamma 1, and I have this one, gamma 2. So these are two curves that give origin to two Lagrangians. And we see that in this case, pi minus 1 of gamma 1 is not Hamiltonian isotopic to pi minus 1 of gamma 2. And the reason why is because for you to isotope the curves gamma 1 and gamma 2, you would have to pass through that point. But that point is there, so you can't do it. Okay? But on the other hand, gamma 1 is can be isotoped through planar curves to this straight line L here. So, and of course, pi minus 1 of L is a special Lagrangian. And pi minus 1 of gamma 1 is Hamiltonian isotopic to pi minus 1 of L. So they are in the same Hamiltonian isotopic class. But what happens if you try to isotope gamma 2 to gamma 1 or to L? So what happens is that you will try to go over that point, but you get stuck there. So it looks like at some point, the curves that you get look like this. So you go around that point, and you are very close to this straight line here, and to this other straight line there, which, by the way, are special Lagrangians. And you have this other, and you have this white curve there, which is which gives you a Lagrangian, which is Hamiltonian isotopic to a Lagrangian connect sum of. Oh, sorry, I should write pi's. I write mu sometimes because of the hyperKahler moment map. But okay, so that's trying to deform gamma 2 until you get to L, you get stuck at some point. And where you get stuck, what you are actually doing is decomposing pi minus 1 of gamma 2 as a Lagrangian connect sum. And it turns out that this configuration destabilizes pi minus 1 of gamma 2, which is not, which you cannot Hamiltonianly isotope to a special Lagrangian. And once you understand these two cases and these two examples, it becomes very easy to simply using logic to give a proof of the first theorem. So it doesn't use any more heavy machinery. It just requires that you sit down and think carefully about all the possibilities. So, and let me say why this destabilizes, just to make that comment. So if you look at this angle here, that is basically the beta of L1. And if you look at the beta of L2, it turns out it's this angle. So in particular, this guy is greater than 0 and this guy is less than 0. So it turns out that beta L1 is greater than beta L2, and that is the condition for destabilizing. Okay, so that's where the destabilization comes from. Okay, so and this eventually leads to a proof of the first theorem. So now let me tell you more or less how the proof of the second theorem goes. So you have this family of Lagrangians, which are pre-images of curves, evolving through Lagrangian mean curvature flow. And this turns out to be equivalent to the curves gamma t evolving through a modified version. I'll call it weighted or just modified. Curve shortening flow. So it's a modified version of the curve shortening flow. And if you look at its properties, one of the properties that it has is that beta t evolves through the heat equation. In particular, its total variation needs to be non-increasing. Is non-increasing, and so it's less or equal than what it was initially, but it started less than pi. So it always remains almost calibrated. So LT remains almost calibrated. And then it follows from work of Lambert, Lotay, and Schulz that for LT applied to our situation. So you apply this to our situation. So this work basically tells you what are the possible ancient solutions to the Lagrangian mean curvature flow that are almost calibrated. So, and you will realize that for LT, which is almost calibrated, to develop a finite time singularity, it needs to hit this discrete set S. Gamma t, so the curve downstairs, must hit S. So this discrete set. But this is impossible because it would violate flow stability. Stability of L naught. And so this means that LT exists for all time. And then it follows from the fact that beta t solves the heat equation and the standard argument that it converges to a straight line, which is the same thing as saying that LT converges to a special Lagrangian. Okay, so this is how the proof goes. And thank you very much for your attention. I am done. Well in time, I guess. Yeah.
All right, let's thank the speaker. Have you got any questions? if not, then maybe I'll ask a question. So
Yes,
so
please.
how restrictive is the assumption then on the? Can you go to the statement of theorem 2?
Yes.
So checking that L0 is flow stable. I mean, have you got examples that sort of illustrate this condition being realized?
Yes. So there are many examples of M4s with the circle symmetry. Basically, what you need to do is that you pick any finite set in R3, and then I can give you many examples that correspond to that finite set, which have different asymptotic geometries. Okay, so the data is you pick k points, pick k a number, and P1 up to Pk points in R3 distinct. So that's then I can construct for you using the Gibbons-Hocking ansatz an M4. Okay.
Mm-hmm.
And then so you have these k points. Okay, so let's say 1, 2, 3, 4, okay. And then I can draw any curve here, any planar curve, connecting points like that, this one, and so on. And that gives me rise to Lagrangians upstairs. If I pick these things to be planar curves. And then the condition that something is flow stable just means that if you want, let's say this curve here is flow stable because if I want to break it apart, I would have to push it to a nearby point, let's say this point there. So to do something like that. And that the total length of this curve, which corresponds to the area of the special Lagrangians upstairs, here, so the length here, is smaller than the sum of the other two lengths. Let's call it then the other two lengths of the first curve, of the curve going from 2 to 3, plus the length of the curve going from 3 to 4. Okay.
Mm-hmm.
And this means that this curve here is flow stable because every time you break it, you increase the total length. Okay, so this is an example of how you find the flow stable curve. And of course, it converges to a special Lagrangian. The special Lagrangian will be this straight line connecting these 2 points.
Mm-hmm.
So it will just stay there and converge to this straight line. So it is very easy to construct examples.
Nice.
Where the conditions are satisfied. It's also easy to construct examples where you will have finite time singularities, but that is part of future work that Jason and I are doing right now.
Okay. Very nice. Have you got any more questions?
Yes. Can I also?
Yes,
go
please.
ahead.
Yeah. So I believe in this setting, all special Lagrangians, which are compact, have to connect the poles together. Is that right?
Have to what? Sorry.
Have to connect the poles, these points, the poles that you have on R3. So these also compact.
Well, if they are circle invariants, yes, certainly yes.
Okay, but I guess they're also non-compact.
Yes, for example, you can pick a straight line going from that point up to infinity, like that. That gives rise to a special Lagrangian that is topologically R2. So it's non-compact.
Okay. Okay, and you haven't looked at the Lagrangian mean curvature flow for non-compact settings, right? Is that right?
No, I have not. I have not in generality. I've thought of some interesting examples. but in general, no. But for example, using these kind of constructions, you can find an example of a non-compact Lagrangian in a non-compact hyperKahler for manifold that has infinite topology, and the Lagrangian mean curvature flows starting at that Lagrangian will have infinite an infinite number of finite time singularities. So you can continue the flow past singularities, but there will be an infinite number of singularities. You can make constructions like that, for example. So there are interesting things about these non-compact Lagrangians also.
Okay, cool. And one last thing, like if I pick like a torus that circles one of these poles, then what happens? Does it just collapse on that point?
Yeah, so in general they collapse. The problem, the reason why I didn't mention them is that they are, because they are not zero Maslov. So if you pick a torus, like if you pick the R3 and you pick here a curve and upstairs you have a torus. So these guys, their Maslov class is different from zero. That means that they cannot be graded.
Okay.
But you can still do Lagrangian mean curvature flow starting at them. But what this also means is that it also implies this Maslov thing being different from zero. It also implies that the Lagrangian mean curvature flow will not preserve the Hamiltonian isotopic class. But anyway, you can still do the Lagrangian mean curvature flow starting at them. And then you get downstairs. This corresponds to a family of curves, gamma t, evolving through that modified curve shortening flow. And you can actually do comparison. So you can do comparison using barriers with the curve shortening flows rescaled by different speeds. And you can get them to collapse to a point in finite time. So what will happen to these? And sometimes you can get explicit solutions even, like if you pick the Clifford torus in R4, or an analog of the Clifford torus in Taub-Knut, you can get explicit solutions of these torus shrinking down to points. You can see those explicit solutions in the paper that Jason and I have.
Okay, cool.
So yeah, but it's an interesting point. And there is still things to investigate if you start with these tori. For example, yes, okay. So I think let's say that you have some singularities like that in S, and you pick a torus like this, which try to understand what happens when does it hit the singularity in finite time, or does it get small? Does it get like this and like this, never hitting it in finite time, and eventually converges to two planes? So I don't know the answer to that question. Will it converge to those two planes, or will it eventually hit one of the singularities first? Yeah, so just to say that. I think, yeah, actually, I think I might know the answer to that if I think a little bit. I think it hits the singularities in finite time. Sorry, that is true. Yeah, okay, that is, I do know the answer to that. Sorry.
Okay, so it's not going to become two planes. No.
This is not going to happen.
Okay.
It will pinch. It will get pinched at some point. It will hit one of the singularities first. In general, it might happen that you get something very symmetric that hits them both at the same time. But what happen is that the torus will get pinched in general, like that, by hitting one of the singularities first. Yeah,
okay.
Sorry.
Okay.
But anyway, there might be questions that one can ask that are not easy to answer and that might be interesting to investigate for tori in this setting.
Nice. Thank you.
You're welcome.
All right. Thank you. So, any further questions? Gonçalo? Well, if not, let me remind you before we say goodbye that the instructions to join on our mailing list or to receive announcements for future talks is